Okay, Namaste. This is lecture 1 of Thermodynamics, which is course ME78 in NPTEL platform. I am the tutor assistant of this course, and I'm Priyanka Rajeev. I am a student of Department of Mechanical Engineering, IIT Kanpur. Today we will be discussing the basic terminology which was introduced in last week's class, and also the revision questions from week 1 we will be discussing today. Now, just an overview of the lectures. It started with the definition of thermodynamics. So thermodynamics is the uh, study of transformation of energy, interconversion between heat and work, and relation between heat and work as per the laws of thermodynamics. So the interconversion or relation is defined by the laws of thermodynamics, which we are going to see, and also what does heat and work. Those definitions will also follow in the coming slides. Now, definition of basic terminology is as follows. So first we will start with system. So what is a system? System is the part of the universe that we are studying. We define everything around us and including us as universe. So a part of the universe will be under our observation when we are, solving a problem. Like for example, you want to solve what is the amount of heat energy that is being released from a hot cup of tea. Then that cup of tea will be our system, and the surroundings, or whatever around that cup of tea will be surroundings. So just like that, system here is the part of the universe that we are studying or observing, and the portion around that will be surrounding, and there will be something separating the system and surrounding, that is called boundary. So the boundary can be open and closed. For example, you can see here it is sort of a closed boundary because it has bounded the system from all direction. But here, if you're seeing, this is sort of an open boundary because the upper side is not covered. For example, a, think of a insulated thermos flask. Okay, so thermos flask will be a closed boundary sort of system where the system which we are studying is the tea or coffee or water, whatever is inside that thermos flask will be our system. And the surrounding will be the table or the room which is the in which we have kept the thermos flask, and the boundary will be the flask itself, right? The material of the flask. And open means it will be our previous example. As per that previous example, it was cup of tea. It is like sort of like open. So sometimes we have to imagine a boundary that will be an imaginary boundary, because sort of like an incessant stick or agarbatti is lit up, and you have kept it there. You want to study the heat being emitted from there. So what part of agarbatti we will be taking? We might keep something of this sort over here, and then we are lighting up it over here. Then we might think of such an area where the smoke or the heat will be over there, and not the entire room. We might not be interested in knowing how the smoke is diffusing into the complete room, right? So I'm talking in both fluid and thermodynamics perspective here. So sometimes for flow we will be thinking about a real or imaginary boundary, so that is also being covered here. Now, system, boundary, surroundings, and universe. So those terms, I hope it is understood to you. And now there is something called open system and closed system and adiabatic system. So these are the three systems. So open system is where both energy and matter can enter or exit the system. Like for example, this suppose you imagine this is a container. So this container is open, that you can pour water or something into it or out of it, or you can heat it or cool it. So that is done. So there it is called an open uh, system. And then you have got a closed system, where you imagine a closed um, container again, or closed vessel. So you have for example, a pressure cooker you have kept on a stove, or a closed lid container which is kept on a heating coil. Then you will have energy interactions, like you can heat up the liquid or the matter inside that vessel. But and you can cool it off also. If you are removing the heating coil, after some time it will cool down to the room temperature. But you cannot pour something in or pour something out of it with that closed lid, right? You have to remove that lid only. So that is something called as a closed system, when um, uh, only energy transaction is happening. Then you have got this isolated system, where neither energy nor matter will be, that transaction won't happen. Like energy or matter cannot enter or exit the system. That is called as an isolated system. For example, what we were thinking about earlier, the thermos flask example, that is a perfect example for an adiabatic system, where thermos flask, why it is the liquid, if it is like hot liquid is kept inside the thermos flask, it is not cooling down, because heat cannot exit. That means energy transaction cannot happen with the surrounding. So that is why it is remaining hot. And also you can see that there won't be a reduction in the quantity of matter also, because matter is also not sort of exiting the system. So that is adiabatic system. Then you've got control mass and control volume. So control mass, uh, okay, so control mass is where you are dealing with fixed amount of matter, fixed amount of matter. uh, that is sort of like an closed system that we are talking about. Closed system, that means energy changes can be there, but no matter change won't be not there. Like you control mass, that means you have fixed the amount of matter which is inside the system. So that is sort of a definition, another way of looking at a closed system. Then you have got control volume, which is where you are fixing the space or volume, fixing volume or space. That means it is an open system. That means, say for example, in the uh, cup of coffee or tea problem, you would see that you can pour the coffee in or coffee out of the cup, right? So matter is sort of like uh, changing, the amount of matter is sort of like changing, so is the energy. So that is another definition of open system, right? So that is why control volume approach of solving a problem means, it is we are considering something as an open system, and then we are solving the problem. Now another definition comes is energy, heat, work, etc., like different forms of energy. So energy, as we have learned in our lower classes, it's a capability of doing work, or I mean capacity to do something, or which is called work. Okay, now heat is a form of energy that is transferred across system boundary due to temperature difference. Say for example, you have got a system over here, and it has got a T1 temperature. and the surrounding is at T2 temperature, and suppose T1 is greater than T2, by virtue of this temperature difference, there will be a sort of a, you know, um, heat transfer that is happening across a boundary, and that is called as the energy transaction that is happening across a boundary, and that is called as heat. Okay. And of course this boundary should not be adiabatic. That means it should permit the energy transaction as in a closed system or an open system. So that is where this energy will flow from the system to the surrounding, and that is called as heat. Now for work, okay, so for heat again we have to talk about the unit of energy. Unit of heat. So heat will have the same unit of energy, which is um, okay so okay, it is sort of represented by Q when we are writing equations and all, and SI unit will be uh, joules. Okay, joules. Okay, and sign convention when we are talking about. So if we are providing heat to the system, so heat to the system, we will be referring to it as positive. Then if heat is going from the system to the surrounding, then it will be uh, negative. Okay, that is the convention that we are seeing. Then work. So work, we as we have learned earlier, it is sort of calculated using this formula, where it is a dot product between force and displacement. So it is the form of energy that is happening, or it is the result of force acting through a displacement. Like because of a force, there is a displacement happening, and um, that energy is called as work, and it is defined, or it is denoted by W. And again, sign convention of work is as follows. So if you are providing, so into a system, if you are providing work, that will be negative, and if you are obtaining work from the system, that will be positive. Okay, now we have something called internal energy. So internal energy, as we know, all all the matter in this universe is made of um, small particles called atoms or molecules. So that will be the smallest particle of which the matter around us is made of, and these particles are in some sort of motion, like for example translation. Okay, then translation means moving, left or right, or in a linear fashion. If an object is moving, that is called translation. Then there is rotation, and then vibration. So vibration is or oscillations of a particle um, around a fixed point. So about a fixed point. So that these three motions will be there for these particles, and these motion is associated with some sort of an energy, which is associated as internal energy. For example, uh, this this whole sort of translation, rotation, and vibration, these are all motion possessed by this molecule. So that motion is what is being scaled as internal energy. This can be sort of measured using the temperature of the system. So we will get an idea about the internal energy possessed by a system using the measurement of temperature. And we sort of take a convention that at absolute temperature or 0 Kelvin, there is no sort of atomic vibrations or translation motion happening to a to the matter in which is kept at 0 Kelvin. So that 0 Kelvin is called absolute zero. That is the temperature at which, by definition, we are taking all the matter at 0 Kelvin will possess no, uh, molecular motion. Okay, it is absolute standstill. So internal energy of the system, we are denoting it with the symbol U. Okay, and again it will have the SI units of energy, which is joule. Okay, even for work it's the same thing. Uh, so all these are different forms of energy that we are discussing. Now kinetic energy and kinetic energy and potential energy, these are sort of like a bulk energy. So bulk means the other one was molecular level, right? Like the particles, we were talking about the smallest particles and the vibrations happening at the molecular level. Now kinetic energy and potential energy, when we are talking about, it is at the bulk level or the microscopic level, where kinetic energy is the energy possessed by moving objects in an inertial frame with velocity, some sort of velocity, let's call it v. So then it will be half mv square. That will be the kinetic energy. That is how we calculate. So if a mass is moving, mass of uh, so mass of mass m is moving with velocity v, then we calculate kinetic energy as half mv square. And if a mass is kept in a uh, field such as a gravity field, uh, then if that mass is at a normal distance, at a distance of z, at normal to the field. For example, this is earth and it has got gravitation field. So in this field, so normal to that field, you you are measuring a distance z and you have kept a mass m over here, then by virtue of this position, this mass will have a potential energy m g z. Okay, so this is kinetic energy and potential energy. So total energy will be the sum of internal energy plus kinetic energy plus potential energy. So this is going to be the total energy value. Okay, so energy of the system, when we are referring to energy of a system, all these three terms will be coming. Okay, now now there is a discussion on two types of approach for calculating, okay, solving the problems based on thermodynamics. One is this classical approach, another is statistical approach. So thermodynamics has got two broad or main divisions. One is classical, another one is statistical. So in classical, we are sort of observing a volume which is large enough so that we can average out the molecular behavior that is inside the system. For example, here if we can see, in classical thermodynamics, we are observing the matter as a whole. Like you are not bothered about individual molecule, like where is it moving or what is it colliding with and all those things. We are not talking about. For example, in statistical thermodynamics, if you are seeing, you have to you are in a place where uh, you can sort of see um, these molecules colliding with each other or colliding with the wall of the container, and how it is interacting with each other, what velocity it is moving across the container, and all those sort of thing. So so when and where to sort of approximate these behavior is defined by something called as a continuum. So continuum and this Knudsen number, these are very sort of important when we are studying fluid mechanics. So that it is quite easy to explain from a fluid mechanics perspective. That is why I'm taking that approach. So continuum. So there is something called in. First of all, I'll define some Knudsen number. So Knudsen number is the is a non-dimensional number which is a ratio of mean free path uh, length to characteristic length. So what is characteristic length? So whichever length we are talking about. For example, in a flow, if we have got a flow and it is a pipe of length L, then that will be the characteristic length. Okay. So here maybe the container size will be a characteristic length. So that length to mean free path length means, so free path is what, uh, between these two molecules. So for example, this is moving with a velocity v1, this is moving with a velocity v2, and if v2 is less than v1, this first molecule is going to collide with the second molecule, and before colliding with the second molecule, how much path length it has traveled, that is coming under free path length. Okay, so free path length means before a molecule is colliding with another molecule, how much it has traveled, how much length it has, how the distance which it has traveled is given by free path length. And for every molecule that will be different, because it's a random motion that is happening with all these molecules. So we sort of take a average approach over here to get a single quantity, and that is where we take mean of all the um, free path length of individual molecule. So that is given by mean free path length. So mean free path length is the average distance traveled by each of the molecule before colliding before colliding with another particle or wall. So that is denoted by lambda. Okay, so if take some of the color. So if this is the mean free path length, then that is denoted by lambda. So it is lambda by L, that is not a number. Okay, so now you can see if L is really large, like the characteristic length is really large, then um, you won't you won't care about this collision and all those things, right? Because there will be a lot of molecules over there, and mean free path length is at the atomic level, like molecular level, that will be very small. It will be like several orders of magnitude lesser than characteristic. For example, we are dealing with centimeters, millimeters, or meters, and molecular level, the path length will be in angstroms, right? Or Yeah, angstrom. So that will be 10 raised to minus 10. So 10 raised to minus 10 to 10 centimeters, 10, that is a huge number that we are looking at. That order is like several um, you know zeros after point, I mean decimal point, it will be there. So that that is sort of a negligible number when we are talking about in our macroscopic world. So that is why we can approximate it out and say that it is safe to say that, okay, we don't need to think about the individual molecular uh, movement. But when we are talking about a very small characteristic length, maybe we are looking into uh, a very tiny system, then this molecular uh, motion will be very prominent, like you cannot neglect it. Characteristic length, if it is of micrometers, or if it is 10 raised to minus 8 meters we are talking about, then this 10 raised to minus 10 is not a small number. Then there we have to sort of uh, take the help of statistical thermodynamics to study the system. So statistical thermodynamics and uh, classical thermodynamics is connected with the concept of continuum, where continuum is a concept where you sort of approximate the whole matter as a uniform system, which does not have an effect of individual molecular uh, movements. Okay, now Knudsen number. Uh, so, what is the sort of Knudsen number that we are looking at here? So, Knudsen number, if it is um lesser, okay, lesser than 0.001, then it is safe to assume continuum. Because you can see length is right, like really large. Characteristic length is very large. That means the denominator is very large. That is how we are getting such a small number. So when characteristic length is at least 10 to the power minus 3 orders higher than mean free path length, then it is safe to approximate it as a continuum. Okay. uh, Now we have another concept of working substance. So, what is a working substance? Working substance is the matter of the system. Okay, the material or matter inside the system which we are studying. That is working substance. So there are two types of substance. One is pure substance and another is pseudo pure substance. So you can see pure substance, pseudo pure substance, and there is one more thing, mixture. Okay, so pure substance means uh, it is made of entirely one element or compound. For example, water. Water is H2O, that is a compound. Okay, so water is entirely made up of H2O. There is no chemical composition difference, right? And you have got copper, metal copper. Okay, or iron. Okay, so these, if you take a iron plate or metal copper, you won't see a difference in chemical composition. So that is like entirely homogeneously one element or one compound, that is called a pure substance. Then what is mixture? Mixture means there will be a a sort of a so there are two mixtures, one is homogeneous and another is heterogeneous. So mixture is different compounds or different elements are mixed together. For example, steel. Okay, steel is a mixture of iron and carbon. Iron is an element, carbon is another element. Okay, so it's a mixture of iron and carbon. But and there is another thing called heterogeneous mixture. uh, for example, if you for example, sand will have a lot of particles like silica is there, then you have got pebbles and all those things. So that is heterogeneous mix. Okay, heterogeneous mix means what? It is not uniform. You can see the separation between two compounds that is mixed into that one. But for in case of steel, you cannot see the difference, right? You cannot see the iron, metal, and carbon, which is present inside the steel. It is completely like uniformly merged together. So that is called as homogeneous mixture. Okay, so homogeneous and heterogeneous mixture. Another very very famous example is air. Okay, air is a homogeneous mixture because you cannot see the mix. So air has got nitrogen, oxygen, uh, nitrogen, oxygen, carbon dioxide, and many other gases, the sulfur dioxide, and all those gases are there. So these gases are present in air, but you cannot distinguish between each of these gases, right? Air is thus treated as a homogeneous mixture. And then there is something in between that is called a pseudo pure substance. So what is a pseudo pure substance? So if you for the sake of calculation, simplifying the calculation, you will be taking some mixtures as pure substance. For example, air. Okay, so air, in most of our thermodynamics related problems, we are treating it as a pure substance, but in reality it is not. So that is why the pseudo is added. Pseudo means false, right? So pseudo pure substance means for it is not a pure substance, but for the sake of calculation we can consider it as a pure substance. For mostly homogeneous mixtures, for the simplification of calculation, we can average out all the properties that they are having, and we can single out because it will have one single property throughout, like it is isotropic in nature. So that is why we take it as a pure substance. We sort of assume it as a pure substance. So air is a very good example in for pseudo pure substance. Mostly specifically dry air. Okay, so dry air is a pseudo pure substance. Then okay, now comes the very important part of um, this definitions. So we have got um, property. So property is also called state variable. I will tell you why it is called state variable later. So property means characteristic of a working substance. Okay, so characteristic of a working substance. So what are the characteristics of working substance? Its temperature, its pressure, its volume, specific volume. Um, so those are some of the characteristics of working substance. For example, if you have got water in a bottle, you will be like asking whether it is cool or hot. That is temperature. Then if it is fizzy or not fizzy, because so fizzy means what? It is pressurized, right? It is pressurized inside a container, and if it is not fizzy, it is not pressurized in a container. Then if it is oil or water, how can you distinguish between that? The density will be different, the viscosity will be different. So these are the properties of the liquid, right? So that liquid is something which is inside the system, so that is a working substance. So that is called property. Property can be of two types. One is intensive, another is extensive. Intensive means independent. So you can see I and I in here for remembering. Independent of amount or size. Okay, so any property, if it is if we are quantifying that property, if we are measuring that property, if it is independent of amount and size. For example, if I have got one bucket of water or one drop of water, the temperature of that water won't be different. The density of that water won't be different. uh, so it is independent of the quantity, so that is called intensive quantity. So I have told the examples also, like temperature or density, then viscosity, those are intensive in nature. Then you have got extensive, that means it depends on the amount, depends on amount or size. So like for example, you have got volume. Volume is extensive property. Okay. So these are the examples of properties. And then you have got state. So what is a state? State can be specified with properties. Okay. State is defined using property. So if you want to define, so state means it is the condition of that working substance. Okay. um, so how is that, if you want to say uh, the condition of the matter inside the bottle, if it is in um, what to say, like if it is hot or cold, if it is high pressure or low pressure, if it is viscous or not, all those things we use these properties, right? So that sort of defines the condition of that matter. So condition of matter is called state, and it is defined using properties. So property sort of defines state, that is why it is called state variable. So properties are sort of like a coordinate for defining, like for example we have got xy axis. Okay. And if you want to define the position of position in this frame of reference, we will use x coordinate and y coordinate, right? Likewise, if we have got two properties in this axis, like property 1 and property 2, then if you define these two properties, then you will get the state of that matter. So that is why it is called state variable. Okay, this sort of acting like a coordinate to define state. Now we have got phase. Phases, the as we know, it is like um, we have like solid, liquid and gas phase. Majorly our matter around us is in solid, liquid or gaseous phase. Okay. Homogeneous system will contain only one phase, only one phase. And heterogeneous system means it will contain more than one phase, more than one phase. Okay. Then we have something called ideal gas law. So ideal gas law is PV equal to nRT, where P is pressure, V is volume, N is number of moles of substance, then R is universal gas constant, and T is temperature. Okay. Now, uh, so this gives a relation between P, V, and T, that is pressure, volume, and temperature. So if two of them is fixed, the third one is fixed, right? That sort of takes us to state postulate. So what is state postulate? State postulate says that if you have got two intensive properties of a substance defined, then the state of the system is completely described. So intensive properties, as you know, is independent of mass or size. Intensive property uh, Okay, so 2 intensive property gives state of substance. That is the state postulate. Okay. uh, so if you, that is why I was saying, in using ideal gas law, you can see P and V means V by N is specific volume, sort of thing, like uh, it is intensive property, then pressure is intensive property, temperature is intensive property. So if you can see P, V by N, and R and T. R is a constant, V by N is an intensive property, pressure is an intensive property, temperature is intensive property. So if you define either or pressure and temperature, then this V by N is defined, so that specific volume is defined. Then if you are defining specific volume and temperature, then pressure is fixed. So you can describe the entire state by uh, just using two intensive properties. So that is what is state postulate. Now you have got uniform state. Uniform state means what? A uniform state means the properties are same in the entire system. Properties of substance is same in entire system. So that gives us uniform state. So in the spatial coordinate, like XYZ, if it is 3D system we are thinking about, then, or in 2D also, this is y-axis, this is x-axis. So in x-axis, along x-axis, all the points, if I measure temperature here, here and here, wherever, whichever point I'm measuring, temperature is going to be constant. Okay, or pressure is going to be constant, or density is going to be constant. So all these values, like whichever, irrespective of the point of measuring, I'll be getting the same value for the properties measured all throughout the system. Then that is called as a uh, uniform state or uniform system. Okay, then you have got steady state. Steady state means what? At any time, if I'm measuring temperature at a particular point, so it changes here. At any position, if I'm measuring, for a particular time, at any position, if I'm measuring uh, for a particular time at any point, then that is uniform system. Okay, uniform system for a particular time at any point. Steady state, it changes. Steady state means what? Steady state means for a particular particular point at any time. So if I am measuring temperature at a point as 50 degrees centigrade, for example, 50 degrees centigrade, if I am measuring after okay, at T equal to T naught, I am measuring this as 50 degrees centigrade. At T equal to T1, it should be 50 degrees centigrade only. If it is T equal to T2 also, it should be 50 degrees centigrade only. That means with time changing at this particular point A, the temperature of that point will be 50 degrees centigrade. So that is steady state. Okay, then again you have got steady state, unsteady state, and quasi steady state. So what is steady state? Steady state means this temperature is, or any property is not changing with time. So that is steady state. Unsteady state means what? With time it is changing. Unsteady or transient. So it is changing with time, any property is changing with time, that is called unsteady or transient state. If the changes look really really small, sometimes we can approximate it to be a steady state. That is where quasi steady state comes. Okay, now we have got something called process. So what is a process? Process means if you want to take a system from one state to another. Okay, so this is property P1 and property P2. Okay, with P1 and P2 we can define state 1 and state 2. Okay, so state 2 is P1 of, okay, state 2 is P1 of 2 and P2 of 2, and then you have got state 1 which is P1 of 1 and P2 of 1. Okay, now if we want to take a system from state 1 to state 2, okay, in any manner, so that transformation from one state to another is called a process. Okay, now we have got two ways to define this one. Either you know how it was transformed, that is when I use this bold line. If I don't know how it happened but I know that there has been a transformation, I use a dotted line. Okay, so why, I'll tell you later. So this is how we sort of denote it in a diagram, uh, in a diagram or a chart. Okay, so this is called a process. Process means so there is some change that has happened to the system. System went from system state 1 to state 2, initial state to final state, and that is shown, that transformation is shown using a process. Okay, or the transformation happened using process. Now equilibrium. Okay, now path is what I'm saying. So it can go from state 1 to state 2 in many ways, right? For example, uh, okay, this is one way. Okay, this is another way, this is another way, right? So this is one way, this is one way, this is one way, this is another way. Okay, you can go like this, and then from there it can go like this, and then from there it can come like this. So there are many ways for the system to go from S1 to S2, right? So these are called different paths. Okay, different path of uh, the process. Okay, now we have got reversible process and irreversible process. A reversible process is a process in which this system goes from state 1 to state 2 in a in a series of process. Okay, so reversible process means the system goes from goes from state 1 to state 2 through a series of states. Okay, so this is intermediate state 1. Okay, intermediate state IS1, IS2, IS3, like that it will go. Okay, so it is going from state 1 to state 2 through multiple well defined states. So that is called reversible process. So it can, if I know the intermediate state through which the system was taken from an initial state to final state, it is easy for me to bring it back to state 1 through the same process. Okay, so process of restoration from S2 to S1 uh, is also easy, and also it will never have a permanent effect on the system. Like for example, if I am bringing the system back from state 2 to state 1, then there won't be a permanent effect which is like left back on the system when I'm doing so. Okay, so the restoration is complete. It is it won't like when this process is like reversed, then there won't be a effect on the system or the surrounding. Then that is called reversible process. Okay, then you have got irreversible process, which is when you take the system from system state 1 to state 2 and then you restore it back. There is some sort of a permanent effect which cannot be restored back from system or surrounding. So that is called irreversible process. Then you have got quasi reversible, where uh, the reversibility, the deviation from reversibility is not so large. Then you can sort of approximate the process into a reversible process, even though it is irreversible, but the deviation is not so large that you can treat it as reversible process. Okay, then you have got cyclic process. So cycle is where you take the system, or a system is undergoing a sequence of process, uh, and then okay, so this is again p1 and p2. So system is in state 1, then it undergoes another state, another a process and reaches state 2, then it undergoes a process and then goes to state 3, then it is again undergoing some process and it is going to state 4, then one more process and it is coming back to state 1. So initial and final state is the same, and it is going through a series of sequence of process. So that is called a cycle or a cyclic process. Okay, uh, then next up is thermodynamic equilibrium. So equilibrium, uh, when we are talking about state and property, then equilibrium is a very important concept. Okay, so uh, whenever we are saying that okay, the state exists or this is the property, then we are saying that is not going to change right immediately, because it has reached that measurement. For example, you have got something like a balance. Okay, a balance, you've got uh, weighing, that weighing blocks over here, which is like standardized blocks, and then you have got a vessel where you're pouring rice. Okay, now you measure that mass. So when you're pouring, this is sort of like moving, right? This will move up and down. Then you will say that this mass is fixed only when this is sort of like stop moving, right? So likewise, so that process is called equilibrium. I mean that phenomena, or when it stops, we say that the system has reached an equilibrium where it is no further change is measured or observed. Okay, so only in all this matter, like for example, when you use a digital thermometer, you might have seen the temperature is increasing, and after a point of time there won't be a change. Like it will be sort of like oscillating about one point, one value of temperature, and then after a point of time it will you know it will be permanent, like that value won't change. So that is when the digital thermometer will sort of say that okay, this is the temperature. Even with mercury also, this will oscillate. After a point of time it won't. So then you will take it out and say that okay, this is the temperature that is measured. So it is the change, it stops to change for some point of time. That is when you say that the system has achieved an equilibrium. Okay, so system uh, can change its state, and that change when it has stopped, or um, that that sort of a change in any property has stopped, that is when you say that that property is fixed. And when the property is fixed, that is when you say that the state is fixed. When the state is fixed, that is when only when equilibrium is achieved, that is when the state is fixed. So it is uh, it both exist together. It is not like one is the causage of another. Cause and effect relation is not there. When you say that the state or the property is there, that means equilibrium is there. Okay, equilibrium is implicitly assumed to exist. Okay, so now how can I say that there is no change in property in the system, or there is equilibrium in the system? So there are um, 3 points when you want to say that there is thermodynamic equilibrium of the system. Okay, one is mechanical equilibrium. So what is a mechanical equilibrium? Mechanical equilibrium is where when the pressure of the system does not change. The pressure of system is constant. Okay, that is when we say there is mechanical equilibrium. Then you have got thermal equilibrium. That is when there is no temperature change. Temperature is constant. Then you have got uh, chemical equilibrium. So chemical equilibrium means what? EQM is short for equilibrium. Okay. Chemical equilibrium means chemical composition is constant. Okay, is constant. That is when we say, okay, this system, when you have got mechanical equilibrium, thermal equilibrium, and chemical equilibrium, all three is like satisfied, or all three conditions are met, only then you can say that our system is in thermodynamic equilibrium. Okay, now we will go to this revision questions. So, what is the difference between an explicit and an implicit property? That is already discussed. Then, is the statement correct? A control mass, system boundary, shape, and volume can change. So, yeah, we were discussing about control mass, right? So, what is a control mass? When mass is fixed. So, control mass means mass is fixed. That means volume can change. Okay. So the statement is correct. Yes, that is the answer. Now, is the air around us a continuum? So that is one question. Okay, this is one question. Air around us a continuum uh, when airplanes cruise at an altitude of 10,000 meter to 13,000 meter above sea level. Okay, is the air around the aircraft a continuum? So we have to see something like, okay, next question also we have to see along with that. Can the stratosphere be considered to be a continuum? So here we have got Earth. Okay, Earth is there. Then atmosphere layers are as follows. Here you have got um, uh, stratosphere. Okay, one second. Okay. Uh, you have got troposphere, which is at around 12 kilometers from Earth. All like all this layer up till 12 kilometers troposphere. Then from 12 kilometer to almost like 50 kilometer, you have got uh, stratosphere. So, stratosphere. Then you have got mesosphere, ionosphere, and exosphere. So around 80 kilometer, there is something called Kármán line, which we assume it is the boundary of space or boundary of Earth's atmosphere. So from there on, it is space. Okay, carbon line. So stratosphere, uh, we take it as 12 kilometer to 50 kilometer. Okay. Hmm. Now you can see that we live in troposphere. Okay, and normally aeroplanes also, it is cruising around 10 to 13 kilometer. That means approximately inside troposphere aeroplanes are moving. So here air is considered to be dense because you can see aeroplane characteristic length is sort of like what in meters, right? Like 100 meter, 200 meter, 500 meter. That is the sort of values that we are sorry, not yeah, 100 meter, yeah, it will be there. So that is the sort of length that we are dealing with. And again, mean free path length is like really really low. So that means the density of air is much high in troposphere, that we can assume it to be having a very low mean free path length, and that means it is a continuum. So it is, answer is yes. Okay, you can assume it to be a continuum. Air around the aircraft a continuum is. Then, can the stratosphere be considered to be a continuum? Again, as the altitude is increasing, the density of air is going to decrease. Okay, so that means what? The density means it's a measure of mass per volume. That means the amount of matter contained in that area. Okay, that is what is measured by density, right? So density means, so how much of matter is contained in that volume. So as we are going higher up the atmospheric layers, you can see that the density is lowering. That means the matter is lowering. That means the molecules, uh, once it was densely packed, all of a sudden it has changed. Okay, there will be very few molecules in that place. Okay, that means what? You have got a larger mean free path length, right? Now it depends on what sort of characteristic length we are looking at. For example, if it is bigger stuff like a aeroplane or jet aircraft and all those things, which is usually flying around in troposphere, we sort of assume it as a continuum only. For jet and all, we will be thinking of, okay, it is cruising in a continuum, and that is how we are calculating the lift and everything. But for something very insignificant or small, for example bird, it is not a continuum, or we cannot we cannot treat it as a continuum. So it depends on the sort of you know purpose for which we are um, taking stratosphere, that we will be mm, approximating it as a continuum or not. That depends on the purpose. Usually for engineering purposes, we will be treating air as continuum in stratosphere. Okay, because engineering scale, um, you know things like aeroplane and all, it is still uh, good to be assumed as a continuum. Now the next question is working substance. Here, write the definition of working substance. Working substance is a fluid or uh, fluid, that means gas or liquid or whatever it is, that is undergoing the thermodynamic process or cycle in a system, so that energy is transferred in the form of heat or work, is called um, working fluid. Okay, working substance. So for example, steam and steam cycle. So steam engine, steam is carrying the heat, right? Then when it expands, it becomes work. So what is playing that role of converting steam heat into work, is that is steam. Steam is a working substance over there. So that is a definition. Then you have got a system. Okay, a system is in equilibrium when which of the following conditions are met. So system is in equilibrium. So what are the conditions for system to be in equilibrium? Mechanical, thermal, and chemical. Right. So here you can see pressure is same everywhere means mechanical equilibrium. So that is met. Then temperature is same everywhere means thermal equilibrium. Okay, that is necessary. So that is also check. Now density is same everywhere. That doesn't mean anything. Then chemical composition is same everywhere. That means chemical equilibrium. So the answer is all of the above except C. Okay, so all three is necessary. Density is same everywhere, even if it is not same. For example, oil and water. Okay, oil and water, you pour it in a container and water will be here and oil will be here because of density difference, but there is no change in chemical composition, there is no thermal change or there is no mechanical change because it will be like laying uh, there just like that. I mean, there won't be any movement or anything after a point of time. Like after once you're pouring, then obviously there will be oil coming up, water going down. Those movements will be there. Given up some point of time, the density change is not going to create any problem over there. So density same everywhere need not be the necessary condition for thermal equilibrium. Sorry, thermodynamic equilibrium. So it's option C. Next is under what condition can a flowing fluid be considered to be in equilibrium? Okay, so and this is from the fluid dynamic perspective that they are seeing. So we will define something like a local thermodynamic equilibrium because you cannot talk about the entire uh, fluid because flow is happening because of pressure difference. So pressure difference means there is no mechanical equilibrium, right? So you can only talk about one fluid element, okay, in that flow. Okay, so fluid element, if you consider this fluid element, the pressure around should be like constant. uh, that means at this point the pressure is same. Okay, pressure is same all the time. At this point temperature is same all the time. So that means what? It should be steady flow. Okay, steady flow means what? There is no velocity change at a particular point with time. Okay, or pressure change at a particular point with time. So that is a steady flow. Then next is steady flow. Then next is uh, yeah, there is no unbalanced driving force. Like that is what I'm talking about. Velocity change is not there means acceleration is not there. Acceleration is not there means there is no unbalanced force is there. So if it is not an accelerated flow, if it is a steady flow, that sort of says that the flowing fluid is in uh, a local thermodynamic equilibrium. Okay, so bulk of the fluid will be moving because of this pressure difference and all, but this individual fluid molecules, fluid elements won't be having a pressure difference or anything that is being locally when we are calculating, you won't see that kind of a difference, that kind of a gradient. Okay, so all the external forces, if it is balanced, like for example gravity, buoyancy, then other pressure forces, inertial forces, everything should be balanced. That is when we say this flowing fluid is in equilibrium. Next is what is the weakness in the statement water is in equilibrium. So weakness is it is vague. You should know how the system is like. For example, if it is a closed container, if it is an open container, for example, if it is an open container, there will be vapor pressure, right? So vapor pressure will be acting above the liquid. And so if it is not in equilibrium, then and if it is an open system, and if it is not in equilibrium, that is when you see boiling or condensation or those phenomena. And I if it is a closed system, then you should know if is any chemical reaction happening, those things, right? So you should say that water is in a closed container at uniform temperature, that ensures thermodynamic equilibrium, as I'm sorry, thermal equilibrium. Then with uniform pressure, that means it is having mechanical equilibrium and there is no chemical reaction, that means it is having constant chemical composition, that means it is in chemical equilibrium. So when water is in equilibrium is said, you don't know if it is thermal equilibrium or chemical equilibrium or mechanical equilibrium, or if it is stated to be in thermodynamic equilibrium. If it is thermodynamic equilibrium, then all three will follow. If it is only having chemical equilibrium, maybe it is having it is a flowing fluid, or if it is a boiling fluid, you don't know about all these things. So water is in equilibrium means what equilibrium? That is the next question that you have to ask. Okay, now 1.9. Okay, is this statement true? A system in steady state is also in equilibrium. It is not. Okay, no, that is the answer. Why? Because steady state means there is no property change at a given location, with respect to time. Okay, but there could be still, heat flowing and all those things, because for example, you have got this constant velocity fluid going in a pipe. Okay, but there will be frictional losses and all those things. There will be pressure drop, there will be heat flowing through those things. So you cannot say that it is in equilibrium. Okay, so steady state doesn't ensure equilibrium. Okay, now next is a state is defined by, answer is thermodynamic properties. So, or state variables. Property, if you say instead of property, you say state variable, that is like very much more clear, right? State variable. Uh, the path of a process is defined by. So, the path of a process is defined by um, the series of states through which the system passes from initial to final state. Okay, I'll write over here. Sorry. 1.1. Answer is okay. What I was saying, the path of a process is defined by uh, the sequence of states through which the system passes from initial state to final state. Okay, initial state. I'll write initial to final state. Now, how many processes are required to make a cycle? So it is like minimum. We will consider it as how many processes are required to make a cycle. How many minimum number of process, okay, are required to make a cycle. So at least two, okay, two is the answer. As you can see, so you've got a chart over here, property 1, property 2 axis. So you've got state 1 and state 2. So if a process is taking from 1 to 2, then at least one more process should be there to take it back from 2 to 1, okay, because in a cyclic process, initial and final state is going to be the same. So one more process, at least one more process should be there which will take it back from state 2 to state 1. So it is 2, okay. And maximum is not defined because you can take a lot of processes to reach S1 again, so that is not defined. What causes flow in a pipe to be irreversible? Because there are a lot of dissipative effects. Okay, dissipative effects, like example, viscous or friction, etc. Okay, frictional losses, like when a flow is going in a pipe, what happen? What happens? Like due to wall friction, there will be um, velocity will be less. It will be slowing down, right? So friction, if a flow is acting like this with velocity v, then frictional forces will be there in wall. And also there is something called, between two layers of liquid there will be something called viscous force, right? Viscous force will act, which will retard the flow. So those forces will be there, that sort of creates a lot of dissipative effect, so that is irreversible. And if something happens like mixing is happening or turbulence is there, then there are other effects also, right? So if in a in one pipe there is this carbon dioxide coming, the other pipe there is water vapor coming, then then it is mixed, then uh, it is sort of non-reversible, right? Or methane is coming, oxygen is coming, it is mixed, and then it is I mean irreversible. You cannot again separate methane and oxygen from the pipe, okay. So that is mixing. Then there is turbulence, because of that again viscous forces will be higher, that there will be again dissipation happening. So flow in a pipe is generally irreversible. Now when a tire or balloon is punctured, the air undergoes an irreversible process. Why? So when a tire is punctured, what is happening? Uh, there will be, uh, you know, energy dissipation through sound or heat, etc. So that dissipation of energy cannot be dissipation of energy uh, cannot be, regained back, regained. So that is why it is a irreversible process. Um, Another way of seeing this is, it is not quasi-static. So when air, so balloon is punctured, it is not quasi-static. Okay, so that means it cannot be, uh, you know, approximated by a series of equilibrium state. It is not reversible process. Means what? It is a quasi-static process means, as for example, this is a piston and cylinder. So this quasi-static means it is infinitesimally small time, infinitesimally small step it will be taking to reach from one state to another state. Okay, so that small step is like barely, like it will go from state 1 to a delta state. What is very small distance it will move, and it will reach another equilibrium position. Then it will go another small step higher, and it will reach another equilibrium state. Likewise, it will go through a series of step to reach S2, series of equilibrium state to reach S2. So that is called a quasi-static state, quasi-static process. And this is not so. You can see that it is happening in a jiffy, in a very minute time. This is happening when a tire is punctured. The whole of the wheel or tire, air inside the tire will be coming out of the flat tube within a second, right? So that is not quasi-static process. Then this is what it is about, like sound and heat dissipation, everything is coming out, and you cannot simply reverse it and bring all the molecules back inside without very huge amount of work. Okay, so that is what is called irreversible. So it is irreversible. Now the next one is, why are mass and volume extensive property but density is not? Okay, so mass and volume depends on the scale or amount of substance. So doubling the size or scale or amount of the substance, mass and volume is doubled. So that is why it is not an extensive property. Sorry, it is an extensive property, but density is not, because when you increase the amount of substance, or uh, if you take a large amount of material, it doesn't matter with the density, because if as long as the same matter, same material is taken, the density is not going to change. Another key uh, I mean, key concept is, when you divide two intensive properties, you will two extensive property, you will get an intensive property. That is a you know thumb rule. Okay, so you have got uh, so 1.15. So ratio of two extensive property by extensive property. So ratio of two extensive property will give you an intensive property. So you can see density rho is mass by volume, where mass and volume both are extensive properties. So the ratio of extensive properties will give you intensive property. So that is why it is density is an intensive property. Now 1.16, when ambient pressure value is needed and it is not specified, then you what will you take? So typically we take 1 bar as the ambient pressure. Now the next one is the statement always true? Absolute pressure gauge equal to gauge pressure plus ambient pressure. So absolute pressure, okay, this is a very important concept. So you've got okay, I'll draw this thing now. Okay, 1.17, 1.17. So you've got absolute vacuum. Okay, so vacuum is, this is vacuum. Okay, so that is pressure equal to 0, whatever it is, 18 if you want to consider, or Pascal, whatever it is. Then you've got atmospheric pressure, right? So this is atmospheric pressure. atmospheric pressure, that means P equal to 180. Okay. Then you have got something, you're measuring 2 points. Okay, one is over here and one is above atmospheric pressure. Okay, you're measuring 2 points, one is below atmospheric pressure and one is above atmospheric pressure. So what is happening is you have something called, or I'll draw it somewhere else. One second. Only diagram I'll do. Okay, so you have atmospheric pressure, vacuum, and two intermediate points. One is here and another one is here. Okay, so this is this is vacuum, vacuum, and this is atmosphere pressure. P equal to 1 atm. This is P equal to 0 atm. Then this is okay. Now we will just measure these. Okay. Now the pressure difference from vacuum to atmospheric pressure is called PATM. Okay, atmospheric pressure. Hmm. Now, when you're measuring from vacuum to any point, it is called absolute pressure. Okay, absolute pressure. Okay, when you are measuring from with respect to atmospheric pressure, it is called gauge pressure. Okay, P gauge. G U. Okay, one second. This is a GAUGE. This gauge pressure. So now there are two gauge pressures. So either you can measure from here to there or from atmospheric pressure to any pressure between vacuum pressure and atmospheric pressure. Okay, so what is the difference between these two gauge pressure? This is negative gauge pressure. Okay, one is positive, one is negative. And you have got absolute pressure, then you have got vacuum, and then you have got atmospheric pressure and gauge pressure. Now the question was what? What was the number? 1.17. Okay. So what was the question? Absolute pressure equal to atmospheric pressure. Okay. Absolute pressure equal to atmospheric plus gauge pressure. Right. Now think of these as two scenarios. Okay. One here, two here. In the first scenario, it is very obvious, like absolute pressure of this one, for example. In first scenario, this is the absolute pressure for this one. This is absolute pressure. Absolute pressure means what? With respect to vacuum, you are calculating. So absolute pressure is here. This is atmospheric pressure. Okay, I will just remove this one so that it is not confusing. So even atmospheric pressure is absolute pressure of atmosphere with respect to vacuum. Okay, so I'm just avoiding that to avoid the confusion. So this is again atmospheric pressure. Now I think it is more easy to understand. So in case 1, what is happening over there? Case 1, absolute pressure is given. Okay, this is absolute pressure, and so this length, the whole length is absolute pressure, and then you have got atmospheric pressure plus gauge pressure, and that is absolute pressure. That is very easy to understand, right? So in this holds in the first one. Okay, first case. What about the second case? Second case also, you have got atmospheric pressure is here. What about plus gauge pressure? So it is plus gauge pressure only, but the gauge pressure value will be negative. Okay, so again, second scenario also, uh, this holds. Second scenario also, this holds, but one second. Okay, this holds, but the only problem is here the negative gauge pressure you have to take. Like it is additionally, but the gauge pressure value will be negative. Okay, so that is the concept of gauge pressure, absolute pressure, and ambient pressure. Okay, ambient pressure means atmospheric pressure. Now, SI unit of mass flow rate. Flow rate means what with respect to time. So mass flow rate means mass is kilogram. So mass with respect to time. Mass flow rate with respect to time means mass is kilogram is the SI unit. In time, SI unit is second. So it is kilogram per second. Uh, so that is done. And one more, this options will have capital K and negative, small letter k. So capital K is Kelvin. Okay, so you should not confuse it. So whenever you're writing units, here also, like the second question is also about that. Kilopascal, what is the unit? So it is small k and big P and a small a. Okay, why? Because when a unit is derived using a scientist name, for example Newton, okay, you will write the unit in small letter. So 1.19 and 1.20 I'm writing over here. So Newton, we will write it as small letter when you are referring to the SI unit, but the symbol will be capital N. Okay, if you write capital Newton, this is scientist, scientist name. It becomes a proper noun. Okay, this is SI unit. This is SI unit. Likewise, if you write Pascal with small p, okay, then that is unit. Then it is when you're writing the unit notation, that is P, capital P and A, and when you're writing the whole name, then you have to use capital P. Okay, when you're adding suffixes like kilo, milli, and all those things, you have to use small k. Small k stands for kilo, and capital K stands for Kelvin. That is again Kelvin. Again, I have to write it as small k and all this. Okay, that is how you're expressing the symbols. Now, every extensive property per unit mass is an intensive property comment. We can connect it with the earlier thing where we were saying about extensive property by extensive property is intensive property. So, with respect to that, okay, so this will have 1.20 also. So, what is the answer? Extensive property. So, mass is an extensive property. So extensive property by extensive property will give you an intensive property. So that is why. Okay. Now 1.21, or in concept wise also, if you think, extensive property means what? It will scale with amount or size. Okay. Now you are dividing it with mass will give you per unit what is that quantity of that property. Okay. Whatever is the property, whatever property it might be, if you divide it by per per mass, okay, then you will get uh, that constant value, which is like multiplied with the mass will give you the entire thing, right? So that constant value is not going to change with mass again. So that is an intensive property. That is how you have to think about the concept. Now next is 1.21. Without a system definition, no problem in thermodynamics can be solved. What is your opinion on this statement? Yeah, so because one thing is like, without knowing this boundary, like up to where you have to observe, up to where you have to measure, those are very important, right? Otherwise universe is very vast, right? You cannot measure the whole expanse of universe. So without system definition, how would you know where to stop the measurement, where to calculate, etc. Second is, without knowing the system boundary, how will you measure the interactions of energy, like work and heat and all these terms that we were talking about, work and heat especially, those are happening at the boundary. So we are measuring heat and work as the energy interactions that is happening across the boundary. So if there is a temperature difference between system and surrounding, then heat will transfer from system to surrounding, and you are measuring it as a um, sort of a phenomena that is happening across the system boundary. So if system is not defined, then how can I measure heat or work? That is not possible, right? So that is why, without a system definition, no problem in uh, thermodynamics can be solved. Yeah. Now, again, the same question. A person says system boundary is such a nuisance, there is no need for it. Or will you have to say to that person to convince that it must be shown? Again, system boundary is important for calculating, mass flow, energy flow, heat flow, etc. Basically the flex. Okay, so you should know system boundary. It can be real or imaginary, but you should define a system boundary to understand or mark the system to be studied. Okay, that is very important. Next is steady state. Steady state means that there is no change in temperature, true or partly true. So steady state means there is no change in temperature, that is partly true. That is partly true. Why? Because other properties can also change. Partly true. Steady state means no change in any property. Any properties. Okay, that is steady state with respect to time. With respect to time, again, that is also missing. So that is the complete statement. Then the last one, an egg put into boiling water is not in equilibrium. Indicate whether the statement is true, false, or partly true with reason. So you can see egg put in water, uh, egg put in water. So egg is here, water is here. Okay. So you can see water temperature and egg temperature will be constant. That is like egg and water temperature is same. That means what? Thermal equilibrium. Like, right, thermal equilibrium. Then water pressure, water and egg pressure is same. Okay, like egg will also have the same pressure at the surface, that the water is having at the same level. So that is also mechanical equilibrium is ensured. Okay, even if this two is we are considering as the um, as attained, like for example thermal equilibrium and mechanical equilibrium, we are saying that okay this is there, then what is happening, this egg is getting cooked. Cooked means what? Denaturing of protein is happening. Denaturing of protein. That is why the liquid form which was inside the egg was changing into a hard substance. So denaturing of protein means what? No chemical equilibrium. So chemical composition is changing, right? Chemical composition is changing. So no chemical equilibrium. That means false. Is an egg put into boiling water is not in equilibrium. That statement is true. Okay, that is true. So that's about it. All the questions are discussed. All the concept that was discussed in last week's lecture is revised over here. If there is any other doubts, we can take it in next class. And also next class we will be discussing week 1 lecture topics. So that's about it. Thank you for attending today's session.